When a computer sees these two numbers, it instantly knows which network this device belongs to. But how does it figure that out? The answer is binary. Stay with me, and by the end of this lesson, you'll understand how a device determines the network from these two numbers, and more importantly, you'll have the foundational information that you need to become a subnetting expert. In the last video, we looked at IPv4 addresses written in human-readable format. We now know that this is called a dotted decimal format. If you missed this video, I will have a link to it in the description, and you may want to start with that video. Moving on for the rest of us. So this is dotted decimal format. But this is not how a computer sees an IP address. What does a computer understand? A computer only understands binary. Everything a computer processes is just a bunch of ones and zeros. Because computers work in binary, IP addresses must also be interpreted in binary. Therefore, you need to learn binary. Don't worry, binary can feel like a lot of confusing and even an ominous concept. But I'm going to show you a simple pattern that makes it much easier to understand and convert decimal to binary and binary to decimal. But first, a little vocabulary, so we all have the same words to talk about what we're learning here. Each decimal number in an IPv4 address is actually just 8 binary bits. So we have 8 bits for each section of a decimal number. Each section is called an octet, and we know which section of the IPv4 address we're talking about because they are numbered from left to right. First octet, second octet, third octet, and fourth octet. Since each section is 8 bits, if we add all 8 bits together, we get 32. An IPv4 address is 32 bits in length. Fortunately for us, bits have a place value pattern that makes it easy for us to convert them from decimal to binary and binary to decimal, and that place value doubles when we move from right to left. So it's actually really easy to understand. If we expand just one of these octets, we can take a closer look at it. So we start over here in the first position and use the number 1. And then for each place value, as we move to the left, we double it. Now, if we take our values here from this section of the IPv4 address we're looking at, the third octet, we have starting on the right a 0, and then a 1, 0, 1, 0, 0, 0, 0. We can just add up the place values where there's a 1, and that converts our binary number to a decimal value. So our place value of 8 plus our place value of 2 add up to 10. This chart right here, this chart is worth practicing. You should practice this until you can write it out quickly and convert decimal to binary and binary to decimal numbers. Many CCNA students, myself included, write this chart on a piece of paper or a whiteboard before they start to do any subnetting problems. This is a good habit to form right now. Now we're going to start using that binary in a few minutes. Just hold. We're going to start using that binary. I promise you. But if you remember from the last lesson that every IPv4 address contains a network portion and a host portion. What we haven't talked about yet is how that the computer and the people working with the computers know which part of the address is the network portion and which part is the host portion, because it's not always the same. Let's take a look at this IPv4 address 10.0.0.0. You tell me which part is the network portion and which part is the host portion. It could be that 10 is the network portion and .0.0.0 is the host portion. Or it could be that 10.0 is the network portion and just .0.0 is the host portion. With only the IPv4 address, you cannot tell, I cannot tell, and the computer cannot tell which part of this IPv4 address is the network portion and which part is the host portion. What we need is another partner for our IPv4 address that defines the network portion and the host portion. What we need is a subnet mask. Sometimes I call the subnet mask the best friend forever, or BFF, of the IPv4 address, because like two BFFs, they always work together. Handily, subnet masks are also written in dotted decimal format. Here we have an IPv4 address with its BFF, the subnet mask. When we combine this IPv4 address with this particular subnet mask, the first 3 octets are identified as the network portion, and then the last octet is identified as the area where we can have our hosts, which include the network ID and the broadcast IPv4 address. Here we have another example. Here our subnet mask is 255.0.0.0. Our IPv4 address is the same as it was in the last example, but in this case, because there's a 255 in only the first octet of the subnet mask, now it's just the first octet of the IPv4 address that is the network portion, and all of the remaining octets are identified as the host portion. You might have been thinking, this is easy. I just look at where I put a 0 in the subnet mask, and that section is the host portion, but that's not always the case. Sometimes there's no 0. Sometimes the 255s aren't 255. And then you cannot tell where the network bits stop and the host bits start. So what are we missing? Well, what we're missing is that we're looking at this in dotted decimal format. And what format does our computer use? Our computer uses binary. Since our computer uses binary, we have to think about this in binary as well. Remember that each octet in an IPv4 address and the subnet mask contains 8 bits. When all of those bits are ones, then our decimal value is 255. So when you see a subnet mask like 255.255.255.0, what that really represents is 11111111, and then 8 ones, dot 8 ones, and dot 8 zeros. This pattern shows us that every part of the subnet mask that has a 1, that part identifies the network bits. So in this example, the first 3 octets represent the network, and the final octet represents the host portion. There is one rule that we need to go over real quickly, because sometimes students get this wrong and it really messes things up. That rule is of the contiguous ones rule. So for a subnet mask, all that means is that all of the ones have to stay together. Contiguous is the official term here, but if you want to think of that word as continuous, you can do that. It might help you remember what this rule means. So what does it mean? We're going to go into a little detail here. It means that starting at the left side of the subnet mask, you can have ones. And then as you move to the right, you can't put any zeros in between those ones. So here we have our subnet mask with its contiguous ones. If we need more hosts in each network, we can go backwards by removing some ones. Or if we want fewer hosts per network, we can move forward with our ones. What we cannot do is skip and put a 0 in between the ones. Then this is no longer a subnet mask. This rule makes it possible for devices to consistently identify the boundary between the network portion and the host portion. To get the full picture, we need to see how the computer uses the ones in the subnet mask to determine the network and the host portions of the IPv4 address. You can see here, I have our IPv4 address written in binary, and here we have our subnet mask written in binary as well. The computer has this information also, and what the computer does is it ANDs, no, this is not mistyped, it ANDs the 2 numbers together. The basic rule for ANDing is that 1 and 1 equal 1, and that's it. Every other combination is 0. So 0 and 1 is 0, 1 and 0 is 0, and 0 and 0 are also 0. So the only rule you need to remember for ANDing is that 1 and 1 are 1. So by ANDing these numbers together, the computer will know that we have a 10.0.0 in the network portion, and then the last octet is available for hosts. While you do not need to perform ANDing on the CCNA exam, understanding the process that devices use is key to understanding how you move the network boundary when you begin subnetting. And moving that network boundary is what subnetting is all about. At the beginning of this lesson, we asked how a device can determine which network an address belongs to. Now you've seen the answer. The device converts the address to binary, applies the subnet mask in binary, uses ANDing to end up with the answer, and that determines the network portion. Where every 1 is in the subnet mask determines the network portion, and then the 0 part of the subnet mask is the host portion. So if you know this process, subnetting can be a lot less mysterious. The best way to get comfortable with this is to practice recognizing these patterns. I've created a free worksheet that you can download using the link in the description. It will help you practice converting addresses to binary and identifying the network portion of an IPv4 address with a subnet mask. In the next lesson, I'm going to introduce slash notation, the shorthand way that engineers use to describe subnet masks. A lot of students have trouble with slash notation, but it's so much easier than anything we've just covered. The next lesson is right here somewhere, and I will also link to it in the description. By the way, I'm Colleen with Mom Teaches Tech, and my goal is for you to learn something about subnet masks today. So I hope you did. Quite honestly, you look like you did, and that makes me very happy. Have a great day, and I hope to see you in the next video.